Hello everyone, my name is Peter Kitanidis. I'm a groundwater hydrologist. We only have a few minutes, so I assume that most of you do not know much about groundwater, so I will try to give you an overview. The motivation, of course, is the solar groundwater project. Here is a photovoltaic water pumping system in Gogma, Burkina Faso. Every day around 10 cubic meters of water are provided by this system for the domestic use of 250 people of the village. Now, how important is groundwater? It's a unique resource with unique challenges. In fact, 98% of all water that is not seawater and is not ice is groundwater. That leaves only 2% for the lakes and rivers and the atmosphere. But it has some unique challenges. The first is groundwater depletion. Aquifers are huge, but they are gradually depleted. For every gallon that we take out, we put back, in many cases, only a tiny fraction of a gallon. And the visible effects of depletion you can see here in this schematic. 50 years ago, groundwater table was high. It was maintaining streams and riparian vegetation, and now we see streams disappearing, not because there is less rainfall, but because the groundwater table has dropped, and we see riparian vegetation disappear. Another big challenge, of course, is groundwater contamination that comes from industrial sources. It comes from agriculture, like pesticides. It could also be from natural sources, like we have clay lenses that contain arsenic, and as we deplete groundwater, this arsenic is coming out of these lenses. We have seawater that is intruding, so all these create problems. In fact, groundwater, once contaminated, is hard to clean up. Now, let's say a few things about the hydraulics of groundwater. Darcy's law is a linear relation, like Ohm's law. The specific discharge is like the electric current, and the hydraulic head difference is like the voltage. Darcy's law states that the specific discharge is proportional to the head gradient. So it's as simple as you could get. However, the main challenge is that groundwater systems are geologically very complex and are hard to characterize. It's very hard to go and see inside the formation and figure out what the properties are. In practice, systems are characterized through pumping tests. In other words, you pump in a well and you record the response, and from that you figure out whether the aquifer has high conductivity and whether the aquifer has high storage coefficients. The problem with that is that it's based on many idealizations of the aquifer system, that the aquifer is homogeneous, isotropic, infinite extent, there is no leakage from top and bottom, things like that. Okay, they vary from case to case, but we always have to have a lot of idealization. Here you see a schematic of the system that we have. So essentially we have a PV generator that gets a pump going that pushes the water up into a tank, and we keep the tank as full as possible while we are providing water. Now, sensors provide new opportunities. We have data-driven input-output models that are calibrated to represent the interactions with the aquifer, the pumping drawdown relation, in other words, right? And the hydraulic system, like losses in pipes and so on. So that gives us an opportunity to replace all techniques. So do we see the twilight of classical pumping tests? These tests were developed for the technological capabilities and prevailing culture of a bygone area. Analytical methods, simple conceptual models. So at the end, we estimate parameters of a phantom formation. In other words, a formation that it's supposed to be isotropic and homogeneous and large and so on. If we are interested in the input-output behavior of a system, let us focus on it and do it right. And in fact, in a class I teach on data analysis methods, we used data from this site to calibrate a model that, in our view, does a better job than the one you would get by calibrating a highly idealized system. All right, so it will change the way we teach hydraulics and we characterize the productivity of wells. Okay, so what I did is in the few minutes that we had, I gave you a quick overview of groundwater, the great promise of solar groundwater, but also the pitfalls. In other words, in many cases, this solar groundwater will last maybe 20, 30, 40 years, but after that we will have to find other ways to provide water because even big aquifers ultimately get depleted. That doesn't happen everywhere, but there are two cases. One case where there is enough replenishment from precipitation, and there are other cases where people find a huge aquifer, but there is not enough water coming back in, so sooner or later it will be depleted. Finally, sensors and computers can revolutionize how we characterize well productivity and aquifer properties. Thank you very much for your attention.